In this video, we're going to go through section 5.3, which is on partial fraction decomposition. All right, so it says in section R.6, we learned how to add and subtract rational expressions. Okay, so here's two rational expressions, and we added them by creating a common denominator. And then with the common denominator, we could combine the two fractions. And the result is this. Now, what we're going to talk about in this section is we want to be able to take any rational expression and go in reverse. So we want to start with something like this and solve for this. And this process is called partial fraction decomposition. Now, note we're just talking about rational expressions. And a rational expression is a ratio of polynomials. Now, why do we want to do this? Well, it's just sometimes you want to be able to do this. Well, when you get to calculus, you'll see in terms of integrating, if you want to integrate something, if we're trying to integrate, let's say this, then we can actually easily solve the integral if we could break it up into two separate pieces like this. Okay, and so again, a rational expression is a ratio of polynomials. And so partial fraction decomposition is strictly dealing with rational expressions. Okay, and so to perform partial fraction decomposition, the official process, you need to have a rational expression where the degree of the numerator is less than the degree of the denominator. Not less than or equal to, the degree of the numerator needs to be less than the degree of the denominator. And so if you start with a rational expression and that's not the case, then the first step is going to be to use polynomial long division to reduce the rational expression down to a form where you have the degree of the numerator is less than the degree of the denominator. Then on that rational expression, you can perform the partial fraction decomposition process. Okay, so now let's say we have a rational expression like this with the degree of the numerator less than the degree of the denominator. Then the first step is we're going to write out that they call it the form or the structure of the decomposition. So you're going to have your rational expression and you're going to say that rational expression is equal to, and then on the other side of the equal sign, you're going to write out the form of the decomposition. And the form of the decomposition is going to be based on the denominator of the rational expression, the denominator only, which the numerator doesn't matter at all. The form of the rational of the partial fraction decomposition is going to be based purely on the denominator. Now, we know from what we learned in chapter 3 that any polynomial can be factored into a product of linear and quadratic factors. And this isn't that hard to do for any polynomial, no matter how complex it is. If we use the factor theorem, the rational zero theorem, etc., any of those tools from chapter 3. Okay, now what is a linear factor? A linear factor is a factor, it's ax plus b. That's a linear factor. So here, this x plus 2, x minus 5, that's a linear factor. With both of those have a equal to 1. All right, now, and a quadratic factor is ax squared plus bx plus c. Okay, and so again, we have the ability to factor absolutely any polynomial into, all linear factors if we allow for imaginary factors. But if we strictly include real factors, then we know how to factor any polynomial into a product of linear and quadratic factors, irreducible quadratic factors. And irreducible just means you can't factor it anymore. And the way that you tell that a quadratic factor can't be factored anymore is you look at the discriminant. So like from the quadratic formula, it's the square root of it's just b squared minus 4ac. The quadratic factor is irreducible if b squared minus 4ac is less than 0, because then the only solutions are non-real. Okay, but that's important to note because in this section, we're going to go over all of the possible scenarios for performing partial fraction decomposition with, just linear factors or linear factors maybe to like a power other than 1, or just quadratic factors, or quadratic factors with a power other than 1, or combinations of these. And so once we learn all these methods, then you've learned all possible scenarios for performing partial fraction decomposition, because you know that any polynomial can be factored into just a product of linear and quadratic factors. Okay, and so the process, just to give you an overview of the process. So if we're trying to perform partial fraction decomposition here, then we look at the denominator. We've got 2 linear factors, and then the form in this case, and we're going to get to more specifics on the form in a second, but the form is a over x plus 2 plus b over x minus 5. That's the form in this case, where you just got 2 linear factors multiplying each other in the denominator. And again, the numerator polynomial doesn't matter when it comes to the writing out the form here. Okay, so we're going to learn the rules. In this section, we're going to learn all of the different rules for all scenarios of linear factors, quadratic factors, or like maybe what if the x plus 2 was squared? You had x plus 2 squared times x minus 5. What would you do then? Or cubed. What would you do if you had a quadratic factor in here? What if the quadratic factor was squared or cubed? We're going to learn how to write out the forms for all the different scenarios, the correct form. Once you have the form written out, and again, that form has nothing to do with the numerator here. So once you have the correct form written out, the next step is you multiply the entire equation by the least common denominator. So here that would be you're multiplying the entire equation by x plus 2 times x minus 5. And what happens is that gets rid of the fractions, and you're left with something like this. And then, okay, so once you've gotten rid of the fractions, they might have skipped some steps here, but you're going to have the left side of the equation is going to be the numerator of the main fraction you're trying to decompose. The right side, okay, no, they didn't skip any steps. The right side is just as shown here. But then what they do from here is they distribute and they bring all of the x terms together, and then factor out the x terms to get all those the constants, like the a and the b in this case, times x. And then they group all of the terms without x's together. And then with that, there's a property that says, okay, so here you got the a plus b is going to be equal to the term that's multiplying the x, the 8. Minus 5a plus 2b is going to be equal to minus 19. If you had an x squared, then you'd set all the terms on the right side that are multiplying the x squared equal to the coefficient on the x squared on the left side. And with that, you get a system of equations, and you can solve. Then you solve for the constants. In this case, it's the a and the b. And then when you have the a and the b, then you come and plug it back in, and you've got your decomposed fraction. Now, there is another way. Once you get to this step here, where you remove the fractions, there's another way you can solve it. And so because this is an identity, that means it's true for all values of x. And so with that, you can choose an x, and the equation is still true, any x you want. And so what you do is you choose an x, like you say, what happens when x is equal to 5? And when you do that, that eliminates this term, and you're left with a single equation with a single unknown, and you can solve for b. Then you can come back and say, okay, what if x is equal to minus 2? And that eliminates the b, then you can solve for a. So that's another way you can solve it. Okay? And so that's partial fraction decomposition. And so the main task is, so yeah, if you need to do polynomial long division as the first step, then you do that. Okay? But once you've got your rational expression that with the order of the numerator must be less than, not less than or equal to, less than the order of the denominator. If that's not the case, you're going to have to do polynomial long division. Then the main step is writing out the correct form, right? You're writing your rational, you have your rational expression you say is equal to, and then you write out the correct form of the decomposition with the constants correct and all that. Okay, so let's talk about now, what are the rules for doing this? Okay, well, again, first of all, you're completely ignoring the numerator of the fraction you're decomposing in this step. You're completely ignoring that. It's all about the denominator. And so the first step is going to be you need to factor the denominator into a product of linear and quadratic factors, either just linear, no quadratic, just quadratic, no linear, or a mixture of both. And remember, no matter what the polynomial is, it can always be factored to strictly a product of linear and quadratic factors. So that's the first step. And we talked about factoring earlier in the course in chapter R. We did a bunch of example problems. So if you need, go back to that part of the playlist. Okay. So, all right. So now we're at the step where we've got the denominator factored. And so what you're going to have is, you're going to have one or more linear factors. Some are just to the 1 power, some maybe to squared or cubed or whatever. And you're going to have some more. Multiplying is going to be potentially some quadratic factors that might be raised, one or more that are raised to different powers. Okay, and so what you're going to do is you're going to look and see what you've got in the denominator. Again, I'll say it again. You're going to once you've factored, you're going to have one or more linear factors multiplying with or no linear factors potentially, but in general, one or more linear factors that are going to be raised to the first power or maybe a non-one first power, like the squared or cubed, etc. And then you'll also, multiplying those potentially, you'll have one or more quadratic factors that could be raised to different powers. It could be just any mix of this. You might only have quadratic factors, maybe just one quadratic factor raised to the second power. It could be any mixture of those. Okay, and so you look at the denominator and you see what you have, and based on what you've got in the denominator is going to dictate what the form is that you're going to run out. Okay, and so it says that here's the rules. Consider a rational expression where the numerator and the denominator are polynomials with real coefficients, and the degree of fx is less than the degree of gx. So you factor the denominator, and then you set up the form for the decomposition. That is, you write the original rational expression as a sum of simpler fractions using these guidelines. Okay, we're going to use like the constants a sub 1, a sub 2, b sub 1. These are all constants. All of these capital letters, capital A's, B's, and C's, and we might even get to D's sometimes. Okay, the linear factors. Okay, so you identify the linear factors. For each linear factor of g of x, the partial fraction decomposition must include the sum. So a1 over ax plus b to the first plus a2 over ax plus b to the second, etc., etc. So what does this mean? So what they're saying is you identify, you say, okay, do I have linear factors in the denominator? How many do I have? Like, do you have just one? Do you have two different ones, three different ones? Okay, and then for each linear factor, like each linear factor is going to have its own form that you're going to have to put. If you've got a linear factor that's to the first power, so if you have, let's say, so 8x minus 19 over x plus 2. You have this linear factor to the first power. All you need to do is you just, for this factor, you're going to put a over x plus 2 and you're done. If you had okay, you got one linear factor here that's to the first power, so you put a. Okay, done. Now you're done with this factor. But you have another factor, so you're going to it's going to have its own form that's going to be written out. This is a linear factor to the first power, so you just put, and now you're done. Now you've accounted for all the factors in the denominator, and you're done. That's it. Okay. Now, if you come to a linear factor and you have, let's say this one is squared. Okay. So what do you do here? Well, okay, you say, all right, you say you've got two linear factors. You come to the first one. Okay. You have a linear factor that's to the first power. So you just do. Now you're done. You're done with this factor. But you have another linear factor and it's squared. And so what it was saying here is what you do in this case is you're going to say plus b over x minus 3, but then you're going to say plus c over x minus 3 squared. And if it was cubed, then you would do plus d over x minus 3 cubed. Like let's say it was cubed. Then you'd have, so you had x plus 2 times x minus 3 cubed. You'd have a over x plus 2 plus b over x minus 3 plus c over x minus 3 squared plus d over x minus 3 cubed. That's how you deal with linear factors. And you come to each factor separately, and each factor on its own is going to have its own corresponding form on the right side. If we had another linear factor or a quadratic factor, then we have to add more to match up with those. Now, again, if there was no linear factors, then you wouldn't have any of these in the form on the right side of the equation. Okay. All right, but if there's other than linear factors, there's only one other type of factor. That's a quadratic factor. What's the corresponding form for a quadratic factor? For each quadratic factor, the partial fraction decomposition must include the sum. Okay, so this is the exact same idea as the linear factor in terms of if you've got a quadratic factor squared or cubed. Okay, so, but all right, well, what is this saying here? So if we had, we could put anything in the numerator, it does not matter. Okay, now if we had this. Okay, now let's say if we also had a linear factor, then we just put, let's say we had this and then x plus 2. Well, then we want to, let's make the form for the x plus 2 would be x plus 2. Now we're done with the x plus 2. Okay, but what do we do with this? What's the form here? Well, for a quadratic factor, what you do is, so we just put the quadratic, like similar like we did here, we just put the quadratic factor in the denominator. Okay, but what we're going to put in the numerator, instead of just one of these constants, we're going to put the next available constant, which is b, and then put x plus, and then the next available constant. And I don't know what the constant notation they use here is, but you could use whatever you want. Like you could use b1s, and maybe here you put b1x plus c1. And they're doing that because, okay, if this was squared, what do we do? Well, okay, we would put, it's similar to the linear factors. We put, so we leave this, but now next we would do and then just dx plus e. Or if we put subscript, then we do like that. And then, and if it was cubed, we would, if this was cubed, then we'd have to add a cubed. And it would be 3x squared minus 7x plus 10 cubed, and then all that under b3x plus c3. And that's it. And then, so once you've got your form, no matter what the form is, no matter how, no matter how complicated it is, the next step is you're going to multiply the entire equation by the least common denominator to remove the fractions. And then you're going to distribute everything, bring all of the x to the first terms together, bring all the x squared terms together, bring all the x cubed terms together, and then like factor all of the constants, factor out the x, then factor out the x squared, then factor out the x cubed, and then you set whatever's factored out of the x to the coefficient on the left side of the equation corresponding to x, etc. Or you could set x equal to something to eliminate constants and then solve for the other constants. You could do that as well. Okay, and also note, like if this was 3x plus 2, then you just write out the linear factor that way. Like, remember, a linear factor is ax plus b. You could have a coefficient that's not equal to 1 here. Okay, and so, I mean, and that's it. In the rest of the section, they just give example problems, but, you know, what we're going to do in the upcoming video or videos, we're going to go through a bunch of example problems that cover all of these different scenarios that we talked about. So there's no need to go through these examples here. Okay, so let's go ahead and get into the example problems.